Okay, we're going to be discussing power series. So up until this point, we have looked at the convergence of series where we've had just numbers. So we've looked at things like this. So you had A1 plus A2 plus A3, so on and so forth. And the question has been consistently, are these terms racing to zero fast enough such that this infinite sum adds to a finite number? And again, these are numbers. So we did things like, for example, the sum from n equals 1 to infinity of 1 over n squared, which was 1 plus, so that's 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, so on and so forth. In this case, we used a test, specifically the integral test, to argue that yes, these terms went to zero fast enough so that this was equal to a finite value, this infinite sum, or I should say sum of infinitely many terms. Now, we are going to generalize a bit and say, what if each one of these terms creates or contains an x? So we're going to introduce a variable into the series now. And that's where we get power series. So a power series about x equals a is a series written like this. So just as before, we have infinitely many terms, but this now you can see is like a polynomial in x minus a of infinite degree. So the question then becomes, what values are fair game that if we plug them in for x, we get a series that's convergent? So this is the key question. And again, you want to think of this as we're generalizing, we're stepping back, we're moving up one level in terms of series. If you plug any given value in, if you plug in x equals 4, you replace all these x's with 4s, then you have a series just like these types of series that we've already spent a couple weeks on. But this is the key question. What are the values that are fair game? What values work? And the answer will always have the following form. The answer will always come in the form of an interval. So the way to think of this is as follows. We're going to have an interval centered at A. And then we're going to have the right endpoint, which is A plus R, and the left endpoint, which is A minus R. And what will happen is that inside this interval, so for any x in this, and this is going to be important, open interval, the power series is absolutely convergent. So if you pick any values in between A minus R and A plus R and plug those in for x in the power series, you get a series that's absolutely convergent. If you pick anything outside of here, so any x outside of the interval, so for x outside the interval, and this time we'll say closed, so A minus R, A plus R, the series diverges. And then further, the endpoints, anything can happen. And this is always the case. Now R, the radius of convergence we call it, R will be strictly, or sorry, not strictly, it will be between 0 and infinity. If this R is equal to infinity, that means you can think of it like the right-hand endpoint is A plus infinity, and the left hand is A minus infinity. It would mean any x on the entire real line will work. If R is 0, that means the right-hand endpoint is A plus 0, and the left-hand endpoint is A plus 0, which means it only works at x equals A. And you can see that here. If you plug in x equals A, that will knock out every term except the first one. So those are the two kind of extreme cases. And then there's the case in the middle, which is what's depicted above, where you have absolute convergence in the open interval A minus R to A plus R, divergence outside of that interval, and then at the endpoints, anything can happen. So the way that we fish this out, given any power series, is with this test for power series convergence. So this more or less walks through the picture that we just looked at. So we're given a power series, and the nice thing about power series is they're working with them is very formulaic. The first thing we do is either the root or ratio test to find that interval. So this interval is determined by the root or the ratio test. That gives us that open interval, A minus R, A plus R, on which the power series is absolutely convergent. So see here, we're doing the absolute convergence test on this power series because you see these absolute value signs here. That gives us the interval and the radius of convergence. Since if R is finite, we need to check the endpoints. And the way you do that is you just take those values, plug them in for x. And the series diverges for any x outside of A minus R, A plus R. All power series questions, when you are asked for the interval of convergence, are done this way. And you'll see how this works with the ratio or root test. And it's actually because the ratio and root tests are inconclusive when rho equals 1 that you have to do kind of the annoying step 2, which is manually check the two endpoints. Those two endpoints correspond to the case when rho is equal to 1 and inconclusive for the root or the ratio test. Okay, so let's see this in action. We'll do several examples. So this is a standard kind of power series question. Find the interval and radius of convergence of this given power series. And remember, it's always good to think about these before we jump in. So the question that any power series exercise like this is asking is, what are the fair values for x that you can plug in so that you get something that is convergent? If you look at this, we have a polynomial in the bottom, just n. If this was a 1 in the top, 1 over n, it would be divergent. In the top, for any given x, what you have is an exponential. So this exponential term on the top will determine the convergence, will determine the interval, because it's this exponential term going to 0 that's going to matter. So that's the idea. And again, the way we do this is with either the ratio or the root test, and either one will work here. So let's use, say, the ratio test. And it's very important to always remember, this is a very common mistake, is people will write this. And the reason that's a mistake is to remember that we're doing absolute convergence test. And so you always need those absolute values. If you forget the absolute value signs, you get into trouble with this type of question. So you always want to make sure to remember that when you're doing this step, you're doing the absolute convergence test for a power series. Okay, and so, I'm sorry, what am I doing? Since we're doing the ratio test, this is what we're doing. So we're doing the ratio test, and again, you always want to make sure to have those absolute value signs here. And so ratio of n plus first term to the nth term. So let's move forward with this. Limit n goes to infinity, absolute value. So for the n plus first term, replace each instance of n with n plus 1. So we have 3x minus 2 to the n plus 1 over n plus 1. And then we're dividing by the nth term, which we get right from the summand from the power series. And now we simplify. So limit n goes to infinity, absolute value. We should pop off 3x minus 2 term here. So we have 3x minus 2 to the n times 3x minus 2 to the 1 over n plus 1. And then dividing by 3x minus 2 to the n over n is the same as multiplying by its reciprocal. So n over 3x minus 2 to the n. Now we cancel where we can. 3x minus 2 to the n's cancel. And this becomes the limit as n goes to infinity of absolute value n over n plus 1 times the quantity 3x minus 2. Now, we note we can rewrite this as the limit as n goes to infinity of n over n plus 1 times the absolute value of 3x minus 2. And we note 3x minus 2 does not involve any n term, which means that can be brought outside of the limit. So this becomes the limit as n goes to infinity of n over n plus 1 times the absolute value of 3x minus 2. And this limit, we can check, is 1. And so this gives us absolute value of 3x minus 2. This means, take a step back and remember what we were doing. We've calculated the rho for the ratio test when we're testing this for absolute convergence. The condition that we want is that this is less than 1. So we set this inequality. We know by the ratio test that if rho is strictly less than 1, then the series is convergent. So this now gives us the inequality, absolute value of 3x minus 2, strictly less than 1. And that's what we'll now focus on. The ratio test gave us that. So let's flush that out. So we have absolute value of 3x minus 2 less than 1. Now we know that that means the same thing as minus 1 is less than 3x minus 2 less than 1. Add 2 to everything. 1 is less than 3x is less than 3. Divide everything by 3. 1/3 less than x less than 1. This gives us our interval. So we have 1 and 1/3. The center of that interval is 2/3. The radius of convergence is half of the distance, or half of the length. So the radius of convergence in this case is 1/3. And so we know the series converges absolutely for all x in between 1/3 and 1. Now we get to the part that takes some time, is we have to now check the endpoints. And again, the endpoints are going to be done manually because for anything outside of this interval, that corresponds to the reverse of this inequality. The case when rho from the ratio test is bigger than 1, and thus you have a divergent series. These endpoints come from the case where you have equality here. That's the case when rho equals 1. And remember, that's inconclusive for the ratio test. So we have to do these one at a time. And so recall our series, 3x minus 2 to the n over n. So we have sum n equals 0 to infinity, 3x minus 2 to the n over n. And we need to handle each of these one at a time. So first, we look at the right-hand endpoint. So let's plug in x equals 1. And all you do is just take that 1 and plug it in for x. And then you're back with a regular series like we've dealt with so far. So we have sum n equals 0 to infinity, 3 times 1 minus 2 to the n over n. Or the sum, n goes from 0 to infinity. Sorry, this sum actually starts at 1, right? That was a mistake because the first term wouldn't be defined. But when we simplify this, we have 3 times 1 is 3 minus 2. So that's 1 to the n, or just 1 over n. And we know this is the divergent harmonic series. So we exclude the right endpoint. So at this right endpoint, we now see that the series is divergent. Now let's check the other endpoint. So the other endpoint is when x equals 1/3. So second endpoint, x equals 1/3. And again, remember, sum n equals 1 to infinity, quantity 3x minus 2 to the n over n. We plug 1/3 in for x. And when we do that, we get the sum n equals 1 to infinity, 3 times 1/3 minus 2 to the n over n. Or sum n equals 1 to infinity, 3 times 1/3 is 1. 1 minus 2 is minus 1. So we have minus 1 to the n over n. And this is actually the alternating harmonic series. If we check this first, remember, any alternating series, the first thing you do, is it absolutely convergent? We look at the sum n equals 1 to infinity, absolute value of the terms, which is the sum from n equals 1 to infinity of 1 over n, which is the harmonic. We just talked about that. This diverges. So we do not have absolute convergence at this left-hand endpoint of 1/3. Well, remember, for any alternating series we have two types of convergence. There's the stronger and the weaker. The stronger is the absolute convergence. We just tested for that and it failed. But that means we have to test for the weaker convergence. So is it conditionally convergent? And remember, we had three criteria. So the first, we look at the terms without the minus 1 to the n. So 1 over n, that's positive. 2, they need to be decreasing. So the n plus first term is 1 over n plus 1. The nth term is 1 over n, which is smaller? Well, the one with the bigger denominator. So the terms are decreasing. And then finally, the limit as n goes to infinity of the terms, 1 over n, is 0. So we have conditional convergence at x equals 1/3. So we include it. Which means the final answer for the question is our interval of convergence excludes x equals 1, but includes x equals 1/3. So we're drawing a square bracket at x equals 1/3, but this is a round parentheses at x equals 1. So our answer is 1/3, 1. That's our interval of convergence. So this is the idea. This is how, in general, we handle convergence of power series. We will do several more examples in part 2 of the power series lecture, but this gets us started.